All right, welcome to part 2 of lesson 3 of understanding graphs. Now we're looking this time at water height versus time. And if we look at this example, we've got Mr. Fox giving his dog Dexter a bath. Now, in all of these, we've got to realize that the water is always coming in constant, at a constant rate, and that in a fairly decent town with a good water system, you turn on your tap and it's going to continue out at a constant rate. And that, so we're going to draw a height versus time graph. So we mean the height of the water over time as the water keeps coming in. Now, this is all very general without any exact minutes. So we're really just doing a rough sketch of what's going on. But if everybody was doing this in isolation, your sketches would all have a similar shape to them. And that because we can't actually do a scale here on the time axis without actual time information. So let's get started. First of all, we still should, we've got each axis labeled, so we could still put a title here. Let's maybe call it Dexter's bath. Now, it's saying that Mr. Fox fills the tub, and we know it's going in at a constant rate, so we're going to have a straight line going upwards, and it really, the steepness of it would really depend on how fast the water's coming out, but even still, it's not going to go up too quickly because bathtubs are fairly large. So we're going to have this line going up over time. So that's, first he fills the tub. Maybe by filling we just mean to that certain height. Then he waits for it to cool. Now again, this amount of time might be different for everybody and how long it would take for it to cool. But while it's cooling, the height is staying the same. So we're going to have a horizontal line during that part. So it's just staying the same. So we've done that one now. Then he puts Dexter in the tub, and as we know, when you place an object into a body of water, the water's going to rise due to disbursement. So we don't know how big Dexter is in that, but it's going to rise and fairly quickly as we put the dog in. Let's hope he just doesn't drop him real quick. Just gently puts him in, so the water level is going to rise. And then he takes his time washing the dog. Now, so the amount of water is staying the same, and the height would be the same, except it could be causing it to stir a little bit as we go. And that, but, so there we've got that horizontal line, and that, but it could be a little bit of wavy coming from the splashing. So we've got him in the tub, and we're taking his time washing. Now he says he drains the tub. Doesn't say he takes the dog out. So he drains the tub. So by draining the tub, and so usually it takes probably a little less time to drain, depending how good your drains are. So we'll have the water going back out. Probably not quite that steep a decline, but everybody would have that same shape. All right, so let's move down the page. Now let's, at the bottom of the page, look at another case where we're looking at a height versus volume situation. So here we've got water coming from a tap at a constant rate, but we see that we've got 3 different containers. They're all got the parallel sides, but there are 3 different widths to the containers. Same height, but different widths. And before jumping in, though, let's look at our graph and why we've got volume on the horizontal and height on the vertical. The height of the water is going to depend on how much water has been put into the vessel. So the height depends on the volume. So we say that the independent variable is going to be the volume of the water, and the dependent will be the height of the water. Now, one thing to note as we're looking at this, we see that we've already been given the graph of vessel A. As water is being poured into it at a constant rate, we see the height, the top of the water, that measurement, we see it increase at a constant rate up to when it's right full at the top. Now, if we were to graph the other two, if we look at B is thinner, so it's going to increase more sharply or steeper and get full quicker, so less volume to it. So we would have that looking like, oh, not having luck with that. Let's go back to this. We would have the graph of B looking like this. Notice the height is still the same, the height of the water, and therefore C, which is wider, it's going to take more water. The volume of water is going to be greater to get to that same height. So it's going to be a less steep line. So that would be C. But we can see that their heights are all the same because the heights of the vessels are all the same. So as the cup gets thinner, the line will get steeper. All right, so let's jump to the next page. Now again, we've got water coming into a container at a constant rate, and over that time that the water is filling up, we're measuring the height of the water. And in this case, we're looking at a container where the sides are not parallel. As the container goes up, the width of the container gets narrower and narrower towards the top. So with a container like this, you should envision that the water level is going to rise more quickly. As water pours into the bottle. And the graph, it's not a constant rate then. It's going to keep getting faster and faster and faster that the height is increasing. So the graph will get steeper, continuously steeper as the volume increases. And the type of graph that you're going to get there then is going to be a curve where it just keeps getting steeper and steeper and steeper like that until the vessel is full. And so that would be our kind of our acceleration curve. So if we move to the next figure, the best way to look at this one is to kind of look at it from the bottom up, because you're filling the container from the bottom up. Here, this container, we see that there's three unique sections to it. The bottom, the first section at the bottom, has parallel sides, but the container is quite wide at that part, at that section. Then we've got it where the sides aren't parallel and they're getting narrower as it goes up. And then the top section, they're parallel again, but it's narrower at that section. So we see that we get our constant straight line in the bottom, but it's wide, so it's not an incredibly steep line. And then it's going to have our acceleration in the mid unit, and then a steeper straight line for the top because that part of the vessel is narrower. So what we're looking for here is at the bottom we could say that this is a straight line, not giving you much room there. this is a curved line for the center part, and an even steeper straight line for the top. All right, we'll go down to the bottom section. And just finishing that top one, if the sides of the bottle are parallel to each other, the graph is a straight line. And if the sides of the bottle are slanted, the graph is a curved line. Now what we're looking for in the bottom is if you had a vessel like A, where you've got the bottom portion parallel sides but wide, and the top section parallel sides but narrower, and that if you think about what that graph is going to look like, the bottom section is going to be a straight line, but because it's wide, it's not going to be as steep as the straight line in the top section. So down here, we've got to look for a graph that's got two straight sections, with the second straight section being more steep. So if we're looking at that, we've got curves here, curves and straight lines, and so it can only be this one. So what we'd want you to do here is above that graph, you would mark A, because it matches with A. So what I'm going to do is I'm going to pause. You should pause the video and see if you can guess which ones match up for the 1, 2, 3, 4, 5 other ones, and that. And once you've got them filled in on your booklet, press play again and see what the answers are. All right, so check your answers against these, and hopefully they're mostly all right, and if not all right. Some of these graphs are a little hard to see that, you got a curve, a deceleration curve, acceleration curve, and then a very sharp straight section. The graphs are so small that sometimes it's hard to see if something is straight in a certain section or if it's curved, but they're distinct enough that you should be able to match up those graphs all right. All right, so that's the end of lesson 3, and that you can attack the textbook homework.